Hi everyone, I'm Tharma and I'll be presenting the paper Quantum and Randomized Algorithms for Non-linearity Estimation. This work was jointly done with Dr. Debajyoti Bera. Boolean functions are indispensable in the current day's computer science, especially in cryptography. So it is important to identify good and bad Boolean functions in order to make secure cryptographic protocols. We can do that by evaluating various cryptographic properties. We'll be talking about one such cryptographic property. The Walsh coefficient of a Boolean function f at a point A is defined as here. Intuitively, you can think of it as the average correlation between the function f and the linear function a dot x. Non-linearity, which is closely related to the Walsh coefficient, is defined as the minimum Hamming distance from f to any affine Boolean function. It can be given as half minus half times the maximum Walsh coefficient. The non-linearity estimation problem can be defined as this. Given a Boolean function f as an oracle, an accuracy parameter lambda, and an error parameter delta, output an estimate of the non-linearity such that the estimate is at most lambda apart from the actual non-linearity and with probability at least 1 minus delta. Now, we try to solve the non-linearity problem by solving a simpler problem called the BOUNDFMAX problem. Problem is, given a Boolean function f as an oracle, a parameter g, a threshold tau, and an error parameter delta, you decide if f at max squared is greater than or equal to tau or less than tau minus g. If it's between them, return anything. Here, f at max means the maximum Walsh coefficient. For the classical randomized algorithm for the BOUNDFMAX problem, we use the Goldreich-Levin algorithm along with the lever-order traversal of the binary tree. So here at each node A, we estimate a quantity PWC at A, which is nothing but the sum of squares of Walsh coefficient at points whose prefix is A. If we find that the estimate is greater than or equal to tau minus epsilon, we add it to a queue, else we go to the next node. For any of the nodes that are in the last level and are in queue, if we find that the estimate is at least tau minus epsilon, we return true, else we return false. The complexity can be deduced as O tilde n by epsilon squared into tau minus epsilon. As for the quantum algorithm, we use a combination of Debajyoti amplitude estimation and amplitude amplification routines along with some zero query subroutines. One can see that when you apply the Debajyoti circuit on all zero input, we obtain a state such that each basis state has an amplitude f at x. Now in the quantum algorithm, we essentially estimate this f at squared x. We store it in a register and we compare that against the threshold tau. Now if the estimate is greater than tau, we set the coin register to 1, else we set it to 0. Now we do all this in superposition over all x's. Now we use amplitude amplification to amplify the probability of obtaining 1. And if we see a 1, we return true, else we return false. The query complexity can be deduced as O tilde 1 over epsilon into square root tau minus epsilon. Now we can use these algorithms for BOUNDFMAX with binary search on the interval 0, 1 to obtain an interval I such that the interval size is at most epsilon and f at max squared belongs to that interval. This would give us a randomized algorithm with complexity O tilde n by epsilon cube and a quantum algorithm with complexity O tilde 1 by epsilon to the power 3 by 2. Now, estimating f at max squared with epsilon accuracy gives us an estimate of nonlinearity with order square root epsilon accuracy. So we set epsilon to be order lambda squared in order to get nonlinearity with lambda accuracy. Then we have an O tilde n by lambda to the power 6 query randomized algorithm and O tilde 1 by lambda cube query quantum algorithm. As for the lower bounds, we use the quantum adversary argument on the problem of deciding if a given function is linear or lambda apart from linear. Using that, we obtain a quantum query complexity of omega of 1 over square root lambda queries and a randomized query complexity of omega of 1 over lambda queries. Since the f at max separation problem can be reduced to the non-linearity estimation problem with no extra queries, the same lower bound holds for the non-linearity estimation problem. Thank you.